Hello, everyone, and welcome. Today, we're going to tackle a super important concept in calculus called continuity. And you know what? Let's think of it like this. We're going to become detectives, hunting for glitches in a piece of code. It's going to be fun. Let's dive right in. You know that feeling, right? It's so annoying. You're watching a YouTube video and bam, it freezes and buffers. Or you're in the middle of a game and your character just glitches and teleports across the screen instead of moving smoothly. Well, that sudden break, that jump, that's exactly what a discontinuity is in math. It's literally a glitch in the flow. So really, continuity is just the math of smoothness. We're talking about functions that are predictable with no weird jumps or buffering. So in this explainer, our mission is to become experts at spotting these mathematical glitches and figuring out exactly why they happen. You ready? Let's do this. Okay, here's our game plan for today. First, we'll get a real feel for what continuity actually is. Then we'll get our main tool, the 3-point check. After that, we'll go hunting for all the discontinuities, learn some cool shortcuts using theorems, and finally, we'll learn how to fix the glitches by solving for unknowns. It's a clear path to becoming a master of this topic. Right, first things first, what is this no buffer rule in math? Let's start with a really simple idea. Your NCRE textbook gives this amazing, simple way to think about it. Basically, if you can draw the whole graph of a function without your pen ever leaving the paper, that function is continuous. No breaks, no gaps you have to jump over, just one smooth, unbroken line. And this just makes it crystal clear, doesn't it? A continuous function is like that perfect, smooth 4K video. It's predictable, one connected line. And a discontinuous function, well, that's our buffering video. The graph literally has a break, or a hole, or a sudden jump. It's a surprise, and it completely ruins the flow. All right, let's get to the main tool in our kit. How do we actually, mathematically, check for these glitches? We're going to use something I like to call the 3-point continuity check. And don't worry, it's not some scary formula, it's just a simple checklist. Now, the official NCRT definition looks something like this. But listen, don't let all these symbols intimidate you. I promise you, this one little line contains a super simple 3-step process, and we're going to break it down right now. You'll see it's way easier than it looks. Here it is, the secret recipe to solve pretty much every continuity problem. We check 3 things. Number 1, where is the function going when we come from the left side? We call that the left-hand limit, or LHL. Number 2, where is it going when we come from the right side? That's the right-hand limit, or RHL. And number 3, what is the actual value at that exact point, f of c? And here is the golden rule, the most important part. For the function to be smooth, for it to be continuous, all 3 of these values, LHL, RHL, and f of c, must be exactly the same. The path from the left, the path from the right, and the final destination have to meet at the same point. If even one of them is different, boom, glitch detected. The function is discontinuous. Simple as that. Okay, that's a really good question. And honestly, this is where most students get a bit confused. Do we really have to do this 3-step check for every single function, every time? Well, the answer is no, and I'm going to show you exactly when you need to pull out this special tool. Pay attention to this, because it's super important. We use this detailed LHL and RHL check for a special type of function called a piecewise function, and we only do it at the boundary points, the exact points where the function changes its rule. Think of these points as the number 1 hotspot for glitches to happen. This is the pattern you'll see in your exams again and again. Okay, let's level up to our next skill, glitch hunting. Sometimes a question won't give you a specific point to check. Instead, it'll just ask you to find all the points where the function is discontinuous. So where do you even start looking? Well, here's your treasure map. Number 1, just like we said, the boundary points of piecewise functions. That's always your first suspect. Number 2, for any function that's a fraction, you have to check where the denominator becomes 0. Like for 1 by x, it's always going to have a problem at x equals 0. And number 3, that special guy, the greatest integer function, has a little jump, a little glitch at every single integer. Now, checking limits all the time can get a bit slow, right? So let's talk about some power-ups. These are theorems that act like amazing shortcuts to help you solve problems way faster. So Theorem 1 is all about basic algebra. It says if you have 2 continuous functions, f and g, and you add them, subtract them, or multiply them, the new function you get is also continuous. Easy, but be careful with division. f divided by g is continuous only if the denominator, g, is not 0. This is a crucial condition that so many people forget, so always check it. And theorem 2 is another fantastic shortcut. It's about composition, which is just putting one function inside another. So if both functions are continuous, their composition is also continuous. Take sine of x squared. We know x squared is a continuous function, and we know sine of x is continuous. So sine of x squared has to be continuous too. See? No limits needed, the theorem does all the work. All right, for our last section, we're going to take it to the next level. Instead of just finding glitches, we're actually going to learn how to fix them. I can almost guarantee you'll see questions that look exactly like this in your exam. They give you a function with a missing piece, usually some constant called k, and they ask you to find the value of k that makes the function continuous. They're basically asking you to fix the glitch. And the method is just our golden rule, but we use it in reverse. You start by saying, okay, for this function to be continuous, I know that LHL must equal RHL. Then you just calculate the LHL and RHL from the function they gave you. These will have the letter k in them. Finally, you just set them equal to each other and solve the simple equation to find k. That's all there is to it. So you see, you're not learning some new, complicated concept here. You're just using that same continuity rule you already know to find a missing piece of the puzzle. You already have the key. You can totally do this. Okay, let's do a super quick recap of our continuity toolkit. First, continuity means smoothness, no breaks, like a perfect 4K stream. Second, our main weapon is the 3-point check. LHL must equal RHL must equal f of c. Third, we use this check at the boundary points of piecewise functions. That's where the action is. Fourth, theorems are our shortcuts for algebra and composition. And finally, to find k, we just force LHL to equal RHL and solve for it. You've got this. And with that toolkit, believe it or not, you've now learned the patterns to solve every single type of continuity problem you'll find in your textbook. It's not about memorizing 100 different solutions. It's about recognizing these few patterns. You are now ready. So I'll leave you with one final thought. We know a continuous function has no breaks. But what about a function with a sharp, pointy corner? Like think of f of x equals mod x. You can draw its V shape without lifting your pen, so it is continuous. But that sharp point at the bottom is a bit weird, isn't it? What does that sharp corner mean for a function? Well, we'll explore that next time when we jump into the world of differentiation. I'll see you then.